Hey everyone. This is going to be very intimate because there are not many of you here. So I have a few demo sections in here. So I thought we can maybe try a little different thing. So every time I have a demo, I'm going to make you give a show of hands how interested you are in this demo. So because there's just such a few of you, I can try to tailor this a little bit better to the audience, if that's all right with you. Also, I've been asked to stay within this small square. Usually, I tend to walk around the stage, but you just have to imagine that. All right, so what is this talk about? First of all, the title of the talk is actually a lie. It's not exactly Spire I'm talking about, which is a library. It's actually more like this. It's three libraries that are concerned here: Cats, Algebra, and Spire. Now, if any of you here have worked with Scala before, some of them may sound familiar, in particular Cats. All three of these libraries are part of a family of libraries that's called Typelevel. And they have basically set out to provide a better functional programming experience for Scala. But don't worry, it's not necessary for you to understand or to have worked with Scala before. The code snippets should be self-explanatory, even if you come not from a Scala background. Right, so let's get started. If you go on GitHub and look at the Spire project, this is what you're going to see. It says that Spire is a library for Scala which is intended to be generic, fast, and precise. So that's a bold claim there. You have three things: generic, fast, and precise, and Spire wants to provide all three of them. So usually if you do some kind of numeric programming languages, you have two of them, maybe only one, and in some languages you have none of them. So it's kind of a bold claim. Now, I personally think the authors of this library have done a reasonably good job at providing all three of them, and I hope this talk will convince you of that too. So the initial work happened by these two people, Eric Aschheim and Tom Switzer, and in 2011 they sat down and tried to draft a proposal to get this library into the Scala standard library. By now they have 60 contributors, and given by the talk that I'm not going to talk about numeric programming in Scala, but in Spire, you can have already guessed that the standards proposal didn't go anywhere, so it's still a separate library. So this is the actual proposal, the original one, and you can see this looks like an academic paper, and that was submitted in 2012, and because it looks like a paper, it surely must be legit, right? So all of that has like a solid foundational underpinning. Now, what's in this library? There's a bunch of things, and this slide roughly mimics the structure of my talk. I'm not going to talk about all of these things, but I'm definitely going to start out with a thing that's called the algebraic tower. And I will explain what I mean by that, and then I will also talk a little bit about different number types that are present in Spire for when you don't just want to use floating point numbers. Now, circling back to the title of this talk, this is the actual relationship between the different libraries. So on top, we have a library that's called discipline, which is used for checking that the implementations are correct. And then you have these cats libraries, which is a general library for functional programming. The name cats is, for people who are not familiar with Scala, it's just a playful shortening of category theory, so categories, and everybody likes cats, so why not add this to your project? And then there's some intermediate library, Algebra and Spire. Now, for the purpose of this talk, it doesn't really matter where the things that I'm going to show you reside. You can just basically import Spire and get everything. And there's a bunch of all of these. There's like a much richer ecosystem around this, and interestingly enough, while Spire itself is not a project that's made by Twitter, there's a library by Twitter which is called Algebra, which also provides some numeric algorithm, which is kind of based on a common shared library. So it is possible to use different numeric programming libraries in Scala and have them interoperate. So I think that's really nice. Okay. Having said that, let's talk about algebra. So I'm I'm a computer science PhD student, or at least I used to be. Algebra is something that, well, algebraic structures is something that I have used a lot for theoretical purposes. And if you go on Wikipedia, this is the definition. It says, algebra is a study of mathematical symbols and the rules for manipulating the symbols. Now, this sounds very abstract, and it's not really clear what these symbols are or what the manipulation of these symbols means, and that is very much on purpose. This definition is abstract on purpose. And why is it so abstract? Because mathematicians use this to discover common properties of various concrete structures. And examples of this would be numbers. So numbers, there are a variety of different kinds of numbers, but all of them to some extent support addition and multiplication. And also all of these different number kinds of things, they satisfy the same properties about addition and multiplication. For example, addition and multiplication is usually commutative, so if you have a plus b, that should be the same as b plus a. And algebra basically gives you tools to reason about these common properties. But also, something that is very much up and coming these days in the programming world also, matrices and vector spaces, which is like the foundational underpinning of any kind of, or of most kinds of machine learning techniques, is from a field that's called linear algebra. So everyone here who has tried to go a little bit deeper into machine learning will probably have encountered linear algebra to some extent. But there's also more funky stuff, lattices and Boolean algebras, for example, which kind of abstract over properties like conditionals on Booleans. Very interestingly, all of these are like stuff that you can imagine like using in your day-to-day programming, but there's also some more fun instances of algebra. So this is one of my favorite examples. These are different knots. And it turns out that you can describe the behavior of knots in an algebraic fashion as well, because there's an entire subfield of mathematics that's concerned with checking whether or not a given knot is actually a knot or not. So if you can pull on both sides and get a straight line, or if you get a knot. And that's kind of interesting, I think. And of course, a hobby that is enjoyed by many people, which are these Rubik's Cubes. Also them, if you want to solve them efficiently, you are going to have to learn a little bit about algebra. All right. So these are two real-life examples of algebras. So it's not just something that the mathematicians came up with that has no practical applications. Okay. So I told you that Spire has support for an algebraic tower, and I'm now going to introduce that tower. Here's the most fundamental building block of any algebraic tower, and this is what's called a semigroup. Now, for people who are not familiar with Scala, this is like a trait is like an interface, right? So in your mind, you can just read that as interface semigroup, and A is an arbitrary type. So this is an interface that describes when a type A is a semigroup, or what a type A has to provide in order to be a semigroup. And in this case, it's very simple. It just has to provide a single method, which is called append. And it's supposed to take two A's and return another A. So that's a very simple method. Obviously, the name append doesn't really say much there. It could also be called concat or plus or whatever. The name doesn't really matter. What matters more is that there is a law or a contract that this append function has to satisfy, which is called associativity. And that means that it doesn't really matter in what order you carry out the append operation. So you have three values, x, y, and z. And when you want to append all of them together, you can either first append y and z, and then append x at the front. Or you can append x and y first, and then append z at the end. And this is something very important. So back in the days when Spark was, or like in the days before Spark, when big data was basically just map reduce, the reduce operation exploited that law, because when you do reduce on multiple different nodes, you get back the results in some way or another, like in not particularly in an ordered fashion, but you also don't want to wait for the first one and then for the second one and then for the third one. So you basically just wait for the results to come rolling in, and then you use these associativity law to be able to restructure the way you reduce all the different values. So that's kind of a really foundational property. Okay, so the next level on top of semigroups are what's called monoids. And a monoid is another interface that extends from semigroup. So it takes semigroup and it adds one more method. And that method here is just 0. So we just need to have some kind of empty element, or neutral element, as the mathematicians like to call it. And there's another contract that comes on top of semigroups, which is that the neutral element is actually neutral. So if you append x and 0, you get x back. And that should be kind of obvious. And also, of course, the other way around also needs to hold, kind of obviously. Right. So these two methods are what makes a monoid, essentially. Now, it turns out that lots of things are such monoids. So these are structure. This is a structure that's really pervasive in computing. But I don't really like most of these computing examples are very boring. So I'm going to use another real-life example, and I'm going to talk about trains. So trains, turns out, are also monoids. Because trains have like this modular structure where you have multiple carriages, and then you can have locomotives also. And these carriages and the locomotives, they are connected by what's called couplers. So you see these small things between the carriages and the locomotive, those are couplers. And it doesn't really matter in what order you couple the trains, you're still going to get the same train, right? In particular, you can take this train and couple it with itself, right? With another copy of the train. So you don't just want 2 carriages, you want like 4 carriages, and you can couple all of this together. Now, it is actually possible to have another locomotive in the middle of a train. That's a perfectly valid train. In particular, if you want to go up somewhere, or if you have 20 carriages, sometimes you need another locomotive. And of course, it doesn't really matter in what order you couple these things together. It all produces the same train. Now, I've given this talk a few times before, and sometimes I get the question like, what is the empty train, right? So there's supposed to be like a 0 element. And yeah, what is the empty train? Well, it's just no train, right? So you can always add nothing to the end of a train, you get the same train back. So that doesn't really change anything. All right. So, but let's get back to some programming examples. Lots of things are monoids. So, of course, train and the coupling operation, and also integers like numbers and the plus operation. Now, this is very important here for integers because integers can be monoids in 2 different ways. So you can have integer addition, and the 0 element is a 0, but you can also have integer multiplication. But then the neutral element is 1, because if you multiply x by 1, you get x back. If you multiply x by 0, you do not get x back. So this is very important that a type could be a monoid in 2 different ways. And I'll get back to that a little later. Now, kind of similar to the train thing would be lists. So if you have lists of element type T, and then you can concatenate these lists, and that also gives you a monoid. And this is kind of where the name append comes from. And then you have the empty list as a neutral element. Now, what you can also do is you can also have maps. You can also treat maps as monoids. So let's say you have a map which has a key type and a value type, and then you want to merge these 2 maps together. You can use the monoid for the value type to produce a new map. All right. So, show of hands, who would like to see a demo about this? How can you merge maps? Okay, that should be sufficiently many. Okay, let's see this. Okay, so this is basically a Scala shell where I've just imported the Spire library. There's nothing else going on in there. So yeah, so this is literally what you can write in your Scala file. Now, let's say we want to have a map of countries and cities, and because we're in Spain, we're obviously going to include some Spanish cities. So let's say we have a map, and the map contains as a key Spain. Now, we're going to give it a bunch of cities, and obviously we would use Marbella. Another Spanish city we could include? Malaga, okay. And because we're on this peninsula, let's also include Portugal. And which Portuguese city should we use? Porto. Okay, let's do this. Now this is just a regular plain old map, and you can see it has 2 keys, Spain and Portugal, and each of these keys has some cities. And now we want to have another map which contains some cities that we have missed before. So let's add some cities to Spain. So give me another Spanish city. I heard Madrid. Right, so this is another map. And now we want to combine these 2 maps to form a larger map that contains all the cities we have mentioned. And obviously they should be associated with the correct country, right? So we don't want a map that claims that Madrid is in Portugal, right? So what we can do is the following. So there's this, Scala has operator overloading. So you can use literally any operator that you want. And basically for this kind of concat operation, the authors of Spire didn't want to reuse plus, because plus kind of it's kind of like for numbers, right? So they put just some bars next to the plus. So this would be cities 1 plus cities 2, and then you get a full map with all the cities that we have mentioned so far. And as you can see, it's just like literally list concatenation in there. And interestingly enough, this works in an arbitrary nested way. So you can have nested maps, like 3 layers nested maps, and you can just use this plus operator and get everything collapsed into a single map, which I find really nice. It saves a lot of boilerplate. And yeah, all of that is possible because you have these monoids here. So the list is a monoid. And then, because list is a monoid, then also a map that maps to lists is a monoid. All right. Now, I told you a lot about structures that are monoids. And I told you also that a lot of structures are monoids, but unfortunately, some structures are not monoids. So integers with addition are monoids, but floating point numbers in addition are not monoids. Now the question is, why are floating point numbers not monoids? Well, sadly, they do not satisfy the associativity law. If you have 3 floating point numbers x, y, and z, then it really does matter in what order you perform these operations. You can't just switch that around. And the reason is rounding. So you can construct cases where, let's say, x and y are very small and z is very big. When you add y and z, you get z back again, and then you add x and the sum of that, you get the same thing back, so it doesn't really change anything. But if you add x and y first, 2 small numbers, to create a slightly larger number, then it might be large enough to influence z. So that's really not that nice, because floating point numbers, they're just like hardware numbers that have to satisfy some constraints. And they're not always good for all the use cases. In particular, when you really require this associativity property, then you shouldn't be using floating point numbers. And Spire has an alternative, which I will show in a moment. Okay, so far we have seen semigroups and monoids. There's one more thing, which is called group. And a group is essentially a monoid that also offers an inverse operation, right? So for addition, it would be just subtraction. For multiplication, it would be division. Okay, now, because you sometimes have addition and multiplication, and you want to do both of these things, in particular if you're in linear algebra, you don't just want to be fixed to one of these operations, Spire provides 2 separate hierarchies. So it provides a hierarchy for additive semigroups, so semigroups where the operation is usually like addition. And then there's also the multiplicative hierarchy, which are semigroups that can be treated like a multiplication. But sometimes you need both of them, so there's a whole bunch of new structures there that combine them together. So there's semi-ring, and then there's this whole another thing of like fields and rings and whatever. And this is not an invention by the Spire library authors. This is something that the mathematicians have provided over the years. So this is from abstract algebra, and these names are just how they are. Like, people have named them like this. To me, it's not entirely clear why they are named like this. I mean, I don't know why it's called ring or field. To me, it doesn't really make a lot of sense. But these are the names in Spire also. And there's also no need to memorize that when you're using this. You can just if you think, okay, I need a plus operation that's associative, and I need a multiplication operation that's whatever, associative, then you can just look up in the diagram which one of these things is the appropriate interface to use. Okay, so this is basically you have this entire hierarchy, and Spire provides you with some default implementation. So you can see here, well, you can have a int, long, big int, all of these usual Java classes, and then you can check that they actually satisfy these properties. So I've shown you the properties of semigroups and monoids, but all of these other things have a lot more properties. In particular, there's properties that combine addition and multiplication. For example, if you have a plus b times z, then you may want to distribute that and have a times z plus b times z. And all of these properties are encoded in Spire. And if you have your own number type that you use because of reasons, then you can just write this in your test file, and then Spire will try to automatically check if all of these properties hold. Okay, so who wants to see how that works? Okay, so let's check that. So this is now based on a Scala library that's called Scala Check. And Scala Check, what it essentially does, you give it a property. You say, well, here's a property that requires 3 integers, x, y, and z. And then Scala Check will automatically generate these inputs for you. So it will try to find x, y, z, and then put it into the property and see if the result is true. And it will just do that a bunch of times. So it's basically like unit testing, but the system generates the unit tests for you to some extent. Right. So let's try and see if the laws for integers hold. Okay, so let's try this again. So this is would be the invocation. So I look at all the laws that come from the ring of integers, and then I just check them. And then, as you can see, a bunch of things are happening. And you see, here are all the different laws. It's listed all the names. So you have some laws about multiplication. You have some laws about addition, which are scrolled out right now. Let's see. I can try to make this a little bit smaller, just for the moment, so that you can see just how many tests there are. I have to make this pretty small to see all the tests, right? So I hope you believe me that there's a bunch of things that are being tested there to really make sure that your code makes just the right thing. Okay, let's make this larger again. Right, and you see next to each of these laws, Scala Check prints that it passed 100 tests, so you can see that it generated 100 different test cases for you and checked it. If you now think that 100 test cases are maybe not enough, you can always tell the system to also generate more test cases than this, in case you want to be even more confident. Now, I told you that floating point numbers violate these properties, so let's see if the system could find that. So I'm going to put a float here, and then I'm asking just to check. And that, boom, some of these properties pass, but some other properties fail. For example, the distributivity law, it failed after 9 passed tests. And we see the inputs x, y, z here. And then if we would try to compute arg0 plus arg1 times arg2, we would get different results depending on what order we do this computation. And you can see the reason here why. So we have one number that's really small, so it's like 10 to the minus 12, and then we have 2 other numbers that are really big, 10 to the 28 and 10 to the 20. And this is the reason why this fails. You have like these numbers that are completely different order of magnitude, and then the CPU will have to round that in maybe unexpected ways. Right. But the philosophy of Spire is that even though floating point numbers do not satisfy these criteria, it will still provide you with all the tools that you need in case you know what you're doing, right? So it would not really be nice to just prevent you from using these floating point numbers. Okay, so this is a nice segue into the next section, which is more about possible substitution for floating point numbers. Why do we even use floating point numbers in the first place? Well, they're really fast. If we want to do any kind of computation, our CPUs nowadays are very optimized towards floating point numbers, and they have been for a very long time. Of course they have to round. Otherwise, they wouldn't be able to be that fast. And you can't put arbitrary numbers into just 64 bits. And it turns out that floating point numbers are a very good trade-off for many purposes, but not for all the different purposes, right? So for example, if you're a bank and you have clients, and these clients have bank accounts, and these bank accounts have balances, right? You need to store these balances somehow. You probably wouldn't want to use floating point numbers for that. You probably would use some kind of fixed point numbers, right? So you'd say, well, I'm storing your balance in like with 5 digits precision or something like that, and it's not 5 digits. It's always 5 digits, right? It's no matter how large your balance is, it's always going to be 5 digits. And the most important point here is that there is no one-size-fits-all number type. So all the different number types have trade-offs. There's no silver bullet, right? You won't find any type in Spire that will just fit for all the purposes. And this is not a problem with Spire. This is like a problem with all the programming languages. Like there's no programming language has like a one-size-fits-all number type. It's just something that you always have to think about depending on your use case. Now, Spire has a lot of these number types, and I just want to pick a few of them and tell you a little bit about how they work and what they do. And maybe if you find some of them very interesting for your use case, then you could also look around in other languages. Are usually also libraries that provide those things. Right. So the first one I want to talk about is rational numbers. And rational numbers, if you remember that from school, it's fractions basically. And fractions have two parts. They have a numerator and a denominator, and you just divide n by d, and both of n and d are just just integers, right? And what's nice about these rational numbers is that you can do a lot of operations on them without rounding. So you can add these numbers together, you can multiply these numbers, and you can compare them, all of that stuff, and you have to do no rounding whatsoever, right? So you could go with computation for a very long time without actually having to round anything. Of course, if you need to compute the sine or the cosine or something, then you need to start rounding. But in principle, there's a long list of things you can do without ever having to lose precision at all, right? So if you are in a use case where you need absolutely 100% precision, then rational numbers would be the way to go. There's one downside, though, with rational numbers, which is they may grow very large, right? So if you have a long-running computation of rational numbers, and let's say, stupid example, you have like 1 divided by 1 plus 1 divided by 2 plus 1 divided by 3 and so on. So 1 divided by n essentially, then eventually the denominator is going to grow very large. So this may be a space leak waiting to happen, right? So if you have floating point numbers, you always can predict this is going to be 64 bits in memory. But with rational numbers, it may just be a megabyte if you have a very long-running computer. Okay, megabyte is maybe exaggerated, but it may just be much larger than 64 bits. Okay, who wants to see rational numbers? Okay. You're very interested in demos. I love that. Right. So for this demo, I need to explain a little bit more about Scala, because Scala has some very flexible syntax, and it also allows libraries to extend syntax. So in Scala, you can write the following. Let's say you're going to rate this talk, right? And you have like 0 to 5 stars, and maybe you thought the talk wasn't perfect, you want to give it like 4 out of 5 stars. You can write it like this. So this looks a little bit like a string that has this extra r in front, and r is a function that's being provided by Spire, and essentially it takes a string and converts it into a rational number. And the way this is set up, it all works at compile time. So if you do something wrong, like if you want 4 divided by 0, you will get an exception. It's not going to work out. Right. But the implementation details of this don't really matter. The point that matters is that these rational numbers can be also input very, very nicely. So you can just type these literals where you want them to have, where you want them to be. And of course, you can just manipulate these rational numbers, and they will do the right thing. And yeah, so all of these rational numbers, they also satisfy the monoid property. So we could define a function that we can just call it twice, and it takes an a and returns a plus a in case a is a monoid, and then we can use these monoids, these rational numbers just like that. So we could have twice the score, and then we would also get 8 divided by 5. And of course, this twice function also works for all sorts of other types. So 3. So this is also a nice thing about Spire, because you have all of these abstract machinery in the background. In principle, you can write your algorithms without any concrete number type. You can just say, well, for this algorithm to work, I just need a monoid, and then you can instantiate that with all the different number types that you would need. And yeah, just to demonstrate that these numbers can become quite large, so let's just say, I'm just going to type this by hand, 1, 3 plus, let's say 1 divided by 5 plus, say do 1 divided by 7, you can see this is already getting pretty large, right? So you have 247 divided by 210, and as you can, and this is just by adding 4 different numbers. So you can imagine the more numbers I add here, the larger this is going to get. So what's the next prime number here? 11, I think, right? So this is growing pretty quickly. So depending on your use case, you may be okay with that or not. Now let's say your computation is done and you want to print a result to the user. Of course, you can't print such a fraction because it's very hard to imagine for humans what a fraction represents. So there's also a function that, so let's give this a name, result. So result is this rational number, and then we can say result dot to big decimal, which will convert it to a decimal representation that you can then present to the user in like whatever precision you want to. So this is basically then the rounding operation here. All right. So let's say we are not satisfied with rational numbers. Let's say we want to compute square roots or powers or trigonometric functions. Surely there must be something that has more features than rational numbers. And the mathematicians would say, yes, of course, we have real numbers, right? So real numbers are really nice because you can do almost anything on them. And the problem is, though, that we can't represent all the real numbers on the computer because we have learned from mathematics that some numbers are they just go on infinitely long, right? So for example, pi, it has infinitely many digits. So it's going to be very hard to store all the digits of pi on a computer because we don't have that much storage. Fortunately, we can get arbitrarily close, right? So we can always try to do some tricks for approximation. And this is a diagram I've lifted from some website which explains the relationship between the different types of numbers. So the smallest box there is the integers we all know and like, and probably like long and int are the types you would use most in your day-to-day programming. Then there's rationals, which is slightly larger. So these are the ones that I've just shown you. And then there's a bunch of more funky stuff between rational numbers and real numbers. Now, what I'm interested here is the box that is called computable. And the name already gives it kind of away. It's like a subset of the real numbers that we can represent on a computer. And it turns out a lot of things are in the subset, right? A lot of numbers that we could be interested in, for example, pi, is in the subset of computable real numbers, and also the trigonometric function. All of them work in the subset of computability. And that's really nice. And there's like a bunch of other stuff that is outside of the computable numbers, and but they're really not, I mean, you see these 3 question marks here, right? They're not really that interesting for day-to-day programming. Great. So how does it work? Like, how can we represent pi with its full precision on a computer? Like, when I first read about this, I thought, like, this is impossible. You can't do that. You need infinite amount of memory. But it turns out you can do that by cheating. And here's what the cheat looks like. So we're defining an interface for real numbers. And this interface has just a single method. And that method is called approximate. And that already kind of hints at what's going on. Because we will never actually store the number pi in memory. What we will store is a function that can compute pi to a desired precision, right? So if I want pi to 10 digits, like I want it precise to be have 10 digits, then I can do that, right? I can do that in finite time. I can give an algorithm that will compute pi to the 10 digits. I could also call that same algorithm with a precision of 100 or 1,000 or 1,000,000. It just will take longer, but it will always give you back an approximation. And that approximation here is represented as a rational number. And interesting enough, what you do is you just build up these real numbers, these functions in memory, and functions take just constant space in memory. And then when you want to represent the value to the result of the computation to the user, you can just round it to the next nearest position that you're interested in. Like, let's say you have a use case where you want, I don't know, like 50 digits. So this is most likely not going to fit into floating point numbers. So you can represent as reals, then do all the computation, and at the end call this approximate function to get it for 50 digits. Okay, so now how can we work with these numbers? Because these are just functions. I mean, how can we add them together? Well, let's look at the plus operation, just as a basic example. So the plus operation takes one real, and it takes two real numbers and produces back a new real number. And when we implement the approximate function for this result, we basically have to approximate both the x and the y a little bit more. We have to be a little bit more precise than what we want to because of rounding effects. So what we say is, like, we have x and y, we approximate x and y with the precision +2. I don't know why it's +2. It probably has a good reason. I would have thought +1 would be sufficient, but it obviously needs to be +2 for some reason. And then we get back this R1 and R2, and then we just use the plus operation on rational numbers. And then we are going to have the precise result, or well, the result as precise as we want to. And it turns out you can represent irrational numbers with this, like pi, and this is a formula that exists in Spire as is, and this is probably copy-pasted from some paper that has explained why pi can be defined like this. So a tan is like a trigonometric function, and it's for some reason 16 times blah 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 1 divided by 5, and so on. And then you have a representation of pi. Now, there's another demo here, but I'm not going to ask because I find that demo so cool that I have to show you. So here's what pi looks like in Spire. So you can see, anyone here who's familiar with Java 8 lambdas? This is like the new lambda representation. So this is like kind of an object in memory that is essentially a function. And all of these are like hash codes from internal JVM details, right? There's no actual number here. If you want, we can now do stuff. So we can say like real.pi plus real.pi, and then we have 2pi, and we still don't have a concrete number. We still have like this funny closure here. Okay, so let's give this a name, 2pi. And now what happens if we want to actually look at 2pi? Well, we have to approximate it somehow. And what you can do is the following. So you can, in reality, the function is not called approximate, it's called toRational. And we can call toRational with the precision we want. Let's say the precision is just 1 digit. Then we get 13 divided by 2, which is obviously a very bad approximation for 2pi. We can also, of course, print this as a big decimal. Right, so 6.5. This is not very precise, right? If we want to have, let's just look at 1pi. Right? So this would just tell you that pi is 3, okay? So this is not very precise. Now, the higher this number is, the better the approximation becomes. So if you put 2 in, you have 3.25. So that's a little better, still far away. Can increase this a little bit more, and we have 3.125. I'm just going to cut this a little bit short. Let's put 10 in here, and then you see this is getting towards a more and more precise representation of pi. Now, I can make these numbers, I can make these arguments even larger than that. So I can put in 100, and I would get this. I would get this. So this is a pretty large fraction, and I can, as you can see, it's still instant, right? I press enter, and I get the result. So this is really not so computationally intensive. Now, the higher I use this number, the longer it was going to take. So this is a slight delay in computing this. But if I put like 10,000 in here, it's a longer delay, right? So now my CPU is really like churning, like trying to come up with 10,000 digits of pi. And eventually it will give you the result, but it's just going to take a while, right? And this is really a nice representation, I believe, because you can trade off speed for precision, right? If you want to have it fast, then you can just use a low precision. But if you want high precision, you need to make it a little bit slower. But you can like arbitrarily choose which trade-off you want to do. Okay, so I don't have a lot of time left, so I'm just going to show you some other cool stuff that's in Spire. For example, Spire allows you to deal with error bounds. For example, if you read data from sensors, like you read the temperature or you measure electricity, then you very often don't get precise results, but you know what the error bounds are. Like you say, well, I'm measuring the temperature within the 0.5 degrees Celsius. And the problem is, if you don't represent it in your program, it's very easy to just move that data around into other parts of the code that doesn't know about these error bounds, and then you may get inexact results and you don't even know that. Now, Spire has a class that's called interval, and basically an interval contains two things. It contains a lower bound and an upper bound. And you would put in like the measurement plus minus 0.5 degrees, for example. And then you can do all the usual operations on these intervals. So you can add two intervals together, and the result is going to be the sum of the lower bounds plus the sum of the upper bounds. And not just that. Spire also allows you to have open and closed intervals. So an open interval basically means that the lower bound and upper bound are not included. And a closed interval would be that both of them are included. You can also have bounded and unbounded intervals. So let's say you know that something is 3 or larger, but you don't know what the end is, so it could be 3 to infinity. This is also possible with this interval arithmetic. Right. So what else? Spire is, what I like to say is, it's full of tools you didn't know you needed. Right? So a lot of the time we think we can just get along with longs and doubles, but there's so much more in Spire that is really useful. For example, there's a type that's called savelong. And what is the point of savelong? Well, it's like big int, but faster. So big int allows you to store arbitrarily large integers, and it's sometimes required, in particular if you're working with identifiers, sometimes they exceed the size of longs. And savelong is now internally a long until it becomes too large and then switches to big int. And the reason why it does that is because addition and multiplication of big ints is really slow, but addition and multiplication on longs is really fast. So it tries to stay within the subset of longs for as long as possible, and then just switches to big int if necessary. Also, there's a type called trillion. So it's a three-state Boolean value, true, false, and null to some extent. And this is kind of nice when you're interfacing with JDBC. Also, it provides you with unsigned machine words. So everyone here who has a C, C++ background then came to the JVM and was wondering, why do I not have unsigned numbers? Well, you can have them. You just need to use the correct library for it. And also, there's natural type, which is an unsigned big int, essentially. And the natural numbers should be used, for example, for database columns when you have identifiers, because they can't be negative, right? So if you have a number that shouldn't be negative, then you should be using something unsigned to represent it. Okay, so far that's all I got. And basically, if you take away only one message from this talk, is that it should be that floating point numbers like float and double are not the only number type that you can use, and it all depends on your use case, and you should always be looking at what kind of precision you need, what kind of efficiencies you need, and then pick the most appropriate number type for that. All right, that's all I got.